Welcome back to ECE 441A, 541A. Hopefully you've at least looked at the passport and seen that it's not necessarily a repeat of a previous passport. It's close. I still need the picture, but you can give me a new picture if you would like. The name maybe has changed, maybe not. And the questions, I think, have actually changed between semesters. That's what I'm hoping. The prerequisite quiz, I'm not expecting you necessarily to study for that. Some people are going, how do I get ready for the quiz, the pre-quiz, the prerequisite quiz? It's really just to sort of wake us up and say, oh, I maybe need to do some studying, or, oh, I can figure this one out. Don't worry, don't stress too much about the prerequisite quiz. I'm really trying to see where you're at relative to our starting location in terms of knowledge. Don't stress about the quiz. It's more important to take it so that we can sort of get a feel for the average level of understanding in the class. Homework number 1, hopefully you haven't been staying up all night waiting for that to be posted. It's still not posted, but hopefully it will in a day or two. It's not due until 10 days into September, so you have some time to complete homework number 1. Today what I want to do is, well, maybe before I even go into today, Monday we talked about this electric circuit, and maybe you already modeled it, maybe you didn't, but in the prerequisite review material module in D2L, there is actually some circuit analysis help. And if you go to one of the bottom links, there's how to write differential equations for electric circuits. And in that particular old lecture, in the middle of it, it talks about that RLC circuit. So if you're really wondering how you might be able to analyze that, that might be somewhere to look prior to going all out and going to the library and checking out 30 different textbooks for circuit analysis. But you should be able to start doing that on your own. What we're doing today is actually, now we're stepping into the mechanical side. So today what we want to do is develop a strategy for coming up with these equations of motion, or these dynamics, and we will use a rectilinear mechanical system. Rectilinear is just meaning straight line. Everything's moving in one direction or in a straight line. It actually, if you can get comfortable with this system, it's what we are playing with in the lab all semester. So we need to be very comfortable with basically just rolling out of bed and knowing how to write down the equations of motion for this particular system. This is what we will be playing with in the lab. The lab is not that advanced. People are saying, oh, what all is involved with the lab? I basically will give you some recipes. Everybody like to cook? Maybe. Well, maybe you won't be happy with the end result that comes out of this, but the lab is essentially a cookbook style lab. You simply follow some instructions, collect the data, and then you go home and analyze that data. And it shouldn't take you that long to execute the labs. That's the idea. I will give you videos, and in those you may actually be able to see me in person writing at a whiteboard. So that dates these videos, but you can try to decide how many years ago that was, whatever. So maybe we need to recapture those, but I explain how to walk through those labs. Then once we find the equations will be in a form of a differential equation. We'll then look at how do we develop a state space representation for that system of equations. And the quotes are on the A because we could have 100 different state space representations, and they could all be for the same system, and they could be equivalent. Then we will move into all integrator block diagrams, which are really just analog computers. If we had an analog computer in the lab, we could go over and interconnect it and solve these differential equations based on this all integrator block diagram that we've built up for a given system. I'm going to give you this modeling approach sort of as an outline that maybe will help guide you, and then once we have that, you can step through that to sort of walk your way through the finding or the writing of the dynamic equations associated with a given system. That's the idea. And the first thing that you want to do is really sort of, where am I relative to the system? I need to probably isolate it, establish some boundaries so that I know exactly what I'm trying to model. That's step one. Define the system and the boundaries. The second step is to actually identify the variables that you're interested in. And in an electrical circuit, what are we typically doing with when we try to define or write the equations that govern the dynamics of an electrical circuit? What do we focus on? What do we hone in on when we're writing the equations that govern a circuit's behavior, if we're doing this in the time domain? Or what's of interest in an electrical circuit? The energy storage devices. And what are those? In this environment, we're doing RLC circuits, circuits that have resistors, inductors, and capacitors. Which of those elements store energy? These aren't trick questions, but coming out of a summer recess, maybe it seems like they're trick questions. But the inductors and capacitors, we're storing energy in the magnetic field on the inductor and in the electric field on the capacitor. We focus on those, and we have through variables, which is the current, and we have across variables, which is the voltage. And in the mechanical analog of that, you can select the force to be a through variable and the velocity to be across, and that makes your analogy between electrical and mechanical seem a little bit more diagrammatically consistent. You can sort of flip-flop which one you use for through and across in a mechanical system, but I sort of prefer to use force as the through and velocity as the across. Then we write in step 3 equilibrium and or, depending on how many variables we have, compatibility equations. Do you remember an equilibrium equation in circuits? What do you do relative to nodes? So sum of currents in equals sum of currents out. KCL. Right? Kirchhoff's current law. That's an equilibrium equation. What about if we're walking around a mesh in a circuit? What's that? That's KVL. That's a compatibility equation. If we wanted to think about this in mechanical terms, we could say, oh, equilibrium is the sum of the forces, and our compatibility we could think of as the sum of velocities. I was going to put V, but then you might think sum of voltages, which is really sort of what KVL is, but it's also velocities in the mechanical sense. Step 4 is we write the physical relations between the variables. In step 3, maybe we just have a sum of forces or a sum of currents. Now we need to write those forces or currents in terms of the variables of interest. In electrical terms, what are the physical relations on inductors and capacitors? You're going to get tired of this answer, right? It's Eli. Eli the Iceman. That's how you remember the physical relationships between current and voltage for inductors and capacitors. And we will work through the physical relations for mechanical systems. F is equal to ma is one that we will use for the inertial force. And that might be a new way of looking at mechanical systems for you that you haven't really thought about before. The spring force, do you remember what that is? What happens with a spring? How's the force change as you stretch that spring? Some constant, a spring constant K times the displacement, isn't it? Kx. And we'll have a similar one for our dash pot or our damping element. And in step 5, we put all of this together to create our differential equations that we want. Here's the infamous mass spring damper system. This is what you need to be very comfortable with for the entire semester. We have a mass, we have a spring, and in that spring, here, when you think of a spring, do you think of a shock absorber on a car? Okay, you need to kind of decouple that a little bit, because the shock absorber on a car has a spring and a way of damping out the oscillation. We're decoupling those. B is our damping capability. That's our dash pot. And K is our spring. So the combination of those is what you might have in a shock absorber. We are decoupling those. We have the spring, which doesn't depend, well, in a shock absorber, you would just have the spring and the damping, but here we're trying to put those in two different places. And we have an applied force F. The very first step that we want to do, and now we'll start walking through this process for this particular system, is create system boundaries. That's step 1. Find the system. Well, this system's pretty easy to find. It's the only thing on the page. So our system boundary really is right here. And those hash marks, those are meaning those are rigidly fixed locations. That's what it means. That right-hand side of the spring is not going anywhere. It's fixed. The left-hand side of the dash pot, that's fixed as well. And this blue, which maybe it looks a little artificial here, is actually step 1. That's now our system boundary. And in this case, it is sort of maybe unnecessary to worry about identifying the system. It's right there in front of us. Step 2 is, what are our variables of interest? And I'm giving that to you now. How do you figure out what variables are of interest in this particular system? What would help you describe the dynamic behavior of this mass spring damper system? Okay, so we have to know all of the coefficient values that are up there. The M, the mass, the K is the spring constant, and B is the dash pot value. I'm assuming those are given. Now, what variables do we need to worry about? Position as a function of time is important. If somebody could tell us the position of that mass, that would tell us a lot, wouldn't it? But in terms of a mechanical system, and when we have a mass, we may need more than just position to figure out the dynamics. And velocity. So we need both of those. If we know the position, and now where do we put that on this system? Where do we label position and velocity? Is it over here? Uh-oh, now I have to learn. Oh, that's right. This one, I have a fancy stylus, so now I can actually just erase. I can turn it upside down and erase. Sorry, I'm just playing with a new toy. We can put the label anywhere. We need to put a relative to that mass. We need to draw a line or put a piece of tape down somewhere indicating where 0 is. And typically for this system, I will just say, there's my 0 line, and I'm going to define x, my position, to be positive moving to the right. And its velocity. The variables of interest then are going to be x, the displacement, and the displacement's derivative, or the velocity. I could have put that 0 line on the leftmost edge of the mass. I could have put it on the rightmost edge. You just have to establish where you're locating 0, and then x and x prime will behave accordingly. Here I'm not going to get hung up on where it is. I'm just going to say, okay, here's where I'm putting the line in the sand. There's my position. There's my velocity relative to that point or that line. What was step 3? Writing the equilibrium equations and compatibility equations. To do that for this mechanical system, can I ask you now, on your own paper, draw the free body diagram for this system? So I'm wanting you now to sketch the free body diagram. And it shouldn't take you that long. I'll give you 1 more minute to sketch that. And you can talk if you want with your neighbor, since we're in this nice collaborative environment with all these table numbers. And you might as well use the toys that are in the classroom if you want. You can grab those whiteboards and be sketching if that helps you think. Did everyone come up with a stab at the free body diagram? How many free body diagrams do we have for this particular system? In a multi-mass interconnected system, we might have many different little free body diagrams that we want to focus on, and typically those will be associated with each of the masses in the system. And if we have points that can move independently in that diagram that maybe don't have a mass associated with them, we can also have a free body diagram for those massless points. if those points can move independently of everything else if you fixed all the masses. Here's a strategy that I'm going to discuss for this system, and try to do it in general, but it's maybe a little bit hard to think about it when I just have the one mass. But if I had multiple masses, to find the free body diagram for this one, I would fix all the other masses and say, let me just focus on one mass at a time. And when I'm doing that, now what I want to do is I say, okay, here's my mass. What happens if I displace that in the positive x direction? What forces are going to be in play or activated if I now move that mass in the positive x direction? What's going to be introducing a force based on this diagram? Anything happening on the right side of that mass? If I tried to move that mass to the right, that spring is trying to apply a force opposing that movement, is it not? What about the dash pot on the left? Think of this as a spring that deals with velocities, but it's now removing energy from the system. Its physical relationship is B x prime, or BV, its force. So if we moved this mass in the positive x direction, what direction would the force due to the dash pot be directed? To the left. So now we have a couple of different forces that we've introduced. We have the spring force. We have the force due to the dash pot. We have the applied force, and maybe what I will do, I'm going to have to do a little bit of training on my own, but let's call that U, because a lot of times we have inputs described as U, and that's not the step input. You'll have to get over that in this control context. Sometimes the input might be a step, but in general it's just U of t. So if that's a U, then I can put that in here for U. Am I done with my free body diagram? It depends on how you think about dynamics and writing the equations. I like to actually now introduce another force called the inertial force that opposes movement of that mass. And then I don't remember or get bogged down with saying sum of forces equal mass times acceleration. I can just sum all of my forces and say it's all taken care of because I've included the inertial force. In this case, if I tried to move that mass to the right, is there some inertia opposing that movement? The mass of that object is that gives me an inertial force that opposes the movement to the right. So I actually have one more force in this free body diagram that I like to put in as a dashed, but this is now the inertial force, F sub I. And that's now all of the forces for this particular mass. If I had a second mass somehow interconnected in that mess, I would fix the first mass and do the same analysis on the second. I would displace it in the positive x2 direction, for example, if we had different positions. And then I would say, okay, what do I have any springs, dash pots? I know I have an inertial force, etc. Is that clear? What I'm trying to communicate? Now that we've done the free body diagram, we can write the equilibrium equation by simply summing the forces. Or we now are doing or working with the equilibrium of forces, and you simply algebraically sum these forces. You say, oh, all of the forces going to the left equal all the forces going to the right. If they were all going to the left, it would equal 0, because there would be nothing going to the right. But in this case, we have some going left, some going right. What do we have? We have F sub I, the inertial force, plus the dashpot force, plus the spring constant force, or the force due to the spring, equaling the applied force U. Question? So what is the inertial force? The inertial force is really just accommodating for mass times acceleration. The inertial force is taking care of some of these forces equaling mass times acceleration. So now, instead of saying sum of forces equal mass times acceleration, we just say sum of forces, and we're already accommodating for the mass times acceleration. That is our inertial force. The inertial force is simply the mass times the acceleration of that object. So the inertial force is just ma. It's mx double prime. That's the inertial force. Okay? All the other, we're not accommodating for friction. So this is now on an ice rink. The absorption of energy is through the dashpot, F sub B. Did that answer your question on the inertial force? It takes a little getting used to, but once you use it, I think, it makes it easier to write the equations. You don't have to be saying, oh, which direction is x, and oh yeah, I need to set those forces all equal to this mass times its acceleration. Well, now it all just works out. If you remember that this particular F sub I, this inertial force, is capital M x double prime, or capital MA, mass times acceleration. This I may call it many different things. This might be the damping force. This is the spring force. And this is the externally applied force. And that's now our equilibrium equation. Step number 3. Cha-ching, we can check that off. Step 4 was converting all of those F's into equations involving x, x prime, and x double prime. Those are our variables of interest, x and x prime, so we're probably interested in the first derivatives of x and x prime. Our equation now we want to be written in terms of externally applied forces, which is U, B, K, X, X prime, and X double prime. Those are the variables we want in our differential equation. So here are our physical relations associated with the variables of interest. The inertial force, F sub I, that is simply mass times acceleration. F sub B, that's B times the velocity. So that force is just a function of the velocity. That's how we're assuming the dashpots will be modeled in this class. Here's our damping force. And if you wanted a shock absorber, it would include the damping and the spring, where F sub K is our spring force, k times x. Step 5 is simply putting all of this together. We substitute for f sub I, f sub b, and f sub k relative to these right-hand sides into the equilibrium equation. And that will then give us our second-order differential equation that describes the dynamic behavior of this mass spring damper system. Doing that, we remember what this equation was. It was the sum of f sub I, f sub b, and f sub k, and that was equal to u. We just put those together, and we end up with m x double prime, and the argument of this is t. I'm suppressing that, plus f sub b, which is b x prime, plus f sub k, which is kx, is equal to u. And now, before you go to bed at night, you might look at that block diagram and just remember this beautiful equation. mx double dot plus bx plus kx is equal to u. This we're going to be using throughout the semester. So we need to get comfortable with it. I'm not comfortable yet with all the wires in the room. There was some force there, and I don't know if I want to model it or not. Questions on that? That's in the time domain. What happens now if we wanted to do this in the frequency domain? What if somebody wanted the transfer function of that mass spring damper system? I want to do this in blue for some reason. This transfer function is trying to describe the dynamic behavior of that system. We're not trying to solve for the time response yet, so we don't need to worry about initial conditions. To find the transfer function, we can simply neglect the initial conditions. We want system behavior description, not the total response solution. Let's now Laplace transform this differential equation, this second-order differential equation, neglecting initial conditions. That simplifies the Laplace transform, doesn't it? Remember, you had to subtract the initial conditions, and you have to go real far back into your memory. Well, you don't have to go as far back as I might have to, but anyway. What's the Laplace transform of equation 5? And just to make it different, let's flip-flop the sides. U is now on the left, the letter U, not U, Y-O-U, but the letter U, you're on the left and the other is on the right. I don't know why, I just decided. So what's the Laplace transform of U of t? It's just a generic signal, this U of t. I haven't told you what it is, so the best you can do is capitalize it. You can take the Laplace transform of little u of t, and it's just going to pop out and be capital U of s. It's that easy. That's the Laplace transform of little u of t. We now have U of s. Now we get into a little bit more interesting expressions. What's the Laplace transform of mx double prime? What's the Laplace transform of a derivative? What happens in the frequency domain when you Laplace transform a derivative? Multiply by s. Now we've taken two derivatives, so we have to multiply by s twice. Or m is a constant. It just slides out through the Laplace transform. We have m s squared capital X of s. Once you've seen that, you can now get the others. bx prime, if we Laplace transform that, is b with one s. I probably shouldn't write it in this order. Maybe it's sb. Sorry. Plus k times x of s. To find the transfer function, we really are looking at a ratio of Laplace transformed quantities or signals. And here we really just have two signals that have been Laplace transformed. The driving force, the applied force, its Laplace transform is capital U of S. That's really the input. The position and all of its derivatives, the position's Laplace transform is just capital X of S. So let's now isolate those by factoring. We have U of S is equal to ms squared plus b times s plus k, all times capital X of S. We're now in a position to find the transfer function. G of S is now capital X of S over U of S. And we put everything else on the other side. So we divide both sides by capital U of S, and we need to divide both sides by the bracketed expression ms squared plus bs plus k. And the transfer function of that mass spring damper system is now 1 over ms squared plus bs plus k. Second order transfer function, which we should have expected since we had an acceleration or a second order differential equation. Questions on that? This one also is probably burned in your memory for the rest of the semester. And we might want to what? Normalize the denominator or make the denominator a monic polynomial, factoring out that capital M. So we have 1 over m upstairs, and downstairs we have s squared with a coefficient of 1 plus b over m s plus k over m. Equivalent transfer function. Let's find a state space representation. For this system. And now, because of, let's say, convention, typically our state space, our state vector is an x. So now, if you'll humor me, I'm going to change my position variable to be z and its derivative. And to make sure everybody's clear, let me just re-sketch what I'm doing. One, I just like to draw these diagrams. Oh, let me change it up just a little. In the lab, we're actually going to have a scaling constant associated with our force. I'm going to introduce that now as a gamma. My force now applied to this mass is going to be capital gamma U, and my position, as I had hinted before, is now z. So z is the displacement or position, and z prime is the velocity. In terms of these variables, the second order differential equation is now gamma u of t equaling m z double prime of t plus b z prime of t plus k z of t. Hopefully that doesn't scare anyone. All I've done is simply replaced the z's, or replace the x's in the previous with z's. And this is now a second order differential equation And I'm trying to find a state space representation, which means that I'm now trying to build up a time domain description in a standard representation that involves matrices. If I have a second order differential equation, I'm looking to find a certain number of state variables. And I'm sure you can't guess how many state variables I'm looking for since I have a second order differential equation. I'm looking for 2. So now I'm looking for 2 state variables. And these state variables actually possess all of the state or all of the information about that dynamical system. The state variables possess the state or condition of this dynamical system or any dynamical system in general. And the idea behind these state variables is if we have the present and future inputs, let's say, well, let me call that inputs in words. Input or inputs. If we have that, in our case, we're calling that u of t, and that could be a vector if we have multiple inputs. And this we know for t greater than or equal to some initial or present input value. If we have all of that information and we know the present time state value, or we know the state at the present time, our state vector is going to be x. X is now a tall, thin column of state variables, x sub 1, x sub 2 in this case. This is a vector where t sub 0 is the present time. If we combine those two pieces of information, that will actually, because we know the dynamic behavior of this state through the state space representation, that allows us to determine all the future state variable values as a function of time. So now we can get x of t for t greater than, well, I guess I called it t sub 0 before. That's the beauty of the state space representation. You give me the initial state vector, and you know or tell me the input now and all times in the future, and I can generate the state for all times in the future. In this case, you can generate all the positions and velocities of that mass in that mass spring damper system based on what you have been given or told what the input force is, u of t, as a function of time. Now to solve or to start creating this state space representation, the strategy that I like to use is to first solve for the highest derivative in that differential equation. This assumes that you have a nth order differential equation. If you had multiple coupled differential equations, you would solve for the respective highest derivative in each of those coupled equations. Here we have a second order differential equation. We solve for z double prime. Let's now solve for the highest power derivative in the differential equation. And in the future, I might just refer to that as the DE. And we may have block diagrams, the BD, for example. But here we have Z double prime of t is now equal to minus B over M Z prime of t minus K over M Z of t plus, and now remember I introduced that scaling factor gamma over M U of t. This is the same exact second order differential equation that we have been playing with all period. Just solved for the highest powered derivative. From this, what we want to do now is extract or create a set of differential equations that are coupled, but we want them all to be first order. We want to now start finding first order differential equations that, if we solve them in a coupled way, will give us exactly the same information if we had solved this second order differential equation. We're now looking for our state space representation, a set of coupled first order differential equations. In this case, we want two first order differential equations, and that will give us the same information that that one second order differential equation did. And for this case, we're going to go ahead and let the first component, that's the one subscript, be the position, and we will let the second state variable component, x sub 2 of t, be the velocity. We're just defining these state variables, x sub 1 and x sub 2. And now we want to find an x sub 1 prime equation and an x sub 2 prime equation based on this equivalence, saying x1 is position, x2 is velocity, and that governing second order differential equation. What we are looking for, or wanting to say now, is that we need an x1 prime equation and an x sub 2 prime of t equation. And we want to write those equations. So that will be on the left-hand side of our equations. And on the right-hand side, we want to only have state variables, no derivatives of state variables, and our inputs. So on the right-hand side, we say in terms of x sub 1 of t, x sub 2 of t, and the inputs, which in this case is u of t. So these are our state variables. I feel like I'm a magician. This is bothering me that thing is not keeping up with my writing, but anyway, we're finished for the day, and my stress level will decrease when I stop the record button, and hopefully everything is recorded. We'll pick up at this point next time, but if you want, you can try to find on your own what is x1 prime and x2 prime in terms of x1, x2, and the inputs u.